Welcome to Chapter 1 of the Chemoinformatics Introduction series. In this lecture, we'll explore how computers understand and process molecular structures. We'll learn about SMILES, the text-based language for representing molecules, in CHI for unique identification, and RDKit, the powerful Python toolkit that brings it all together. By the end of this chapter, you'll be able to convert any molecule into a computer-readable format. Chemoinformatics sits at the intersection of chemistry, computer science, and data science. It's the discipline of using computational methods to solve chemical problems. The field emerged in the pharmaceutical industry, where researchers needed to manage and analyze millions of chemical compounds. Today, chemoinformatics powers drug discovery through virtual screening, materials science through property prediction, and environmental science through toxicity assessment. Think of it as giving computers the ability to understand chemistry the way chemists do. SMILES stands for Simplified Molecular Input Line Entry System. It's a way to represent molecular structures as text strings. The beauty of SMILES is its simplicity. Ethanol, which is the alcohol in beverages, becomes just 3 letters. CCO-benzene, the famous aromatic ring, is written as C1CCCCC1, where the lowercase c indicates aromatic carbons and the numbers mark where the ring closes. Even complex molecules like caffeine can be represented as a single line of text. This text representation is crucial because it allows molecules to be stored in databases, searched, and processed by computers. Let's break down the SMILES rules. Atoms are written as their element symbols: C for carbon, N for nitrogen, O for oxygen. Uppercase letters mean aliphatic atoms, while lowercase means aromatic. Bonds are mostly implicit for single bonds, but we use equals sign for double bonds and hash for triple bonds. Branches are shown with parentheses, like CCC, C for isobutane. Ring closures use numbers. C1CCCCC1 means carbon 1 connects back to close the ring. Charges go in brackets. Ammonium ion is NH4+ in brackets. These rules might seem complex at first, but they become intuitive with practice. While SMILES is great for representation, it has a problem. The same molecule can have multiple valid SMILES strings depending on where you start drawing. This is where InCHI comes in. InCHI, the International Chemical Identifier, provides a unique canonical representation for every molecule. It's structured in layers. The main layer contains the molecular formula and atom connectivity. Additional layers encode stereochemistry and isotopes. The InCH key is a fixed-length 27-character hash that's perfect for database searches. Think of SMILES as a description and InCHI as a fingerprint. One molecule, one InCHI always. At its core, a molecule is a graph. Atoms are nodes and bonds are edges. This graph theory perspective is what enables computational analysis of molecules. When we convert caffeine into a graph, each atom becomes a node with properties like element type and charge. Each bond becomes an edge with properties like bond order. We can represent this as an adjacency matrix, where rows and columns are atoms and entries indicate bonds. This mathematical representation allows us to apply powerful graph algorithms, finding rings, calculating paths, measuring similarity. Machine learning on molecules often works directly with these graph structures. Stereochemistry is about the 3D arrangement of atoms, and it matters enormously in drug design. Consider thalidomide. One form treats morning sickness, the other causes birth defects. SMILES encodes this 3D information in 1D text. For double bonds, we use forward and backslashes to indicate E and Z isomers. C/C equals C/C for the E isomer, C/C equals C/C for the Z isomer. For chiral centers, we use @ symbols. 1 @ sign for counterclockwise arrangement, 2 for clockwise. Getting stereochemistry right is critical because proteins and enzymes are highly stereoselective. RDKit is the Swiss Army knife of chemoinformatics. It's an open-source Python library with over 200 functions for molecular manipulation. With just a few lines of code, you can read molecules from SMILES strings, calculate hundreds of molecular properties, generate fingerprints for similarity searching, perform substructure searches, create publication quality visualizations, and generate 3D conformers. The basic workflow starts with importing RDKit's chem module, then creating a molecule object from a SMILES string using mol from SMILES. From there, you can access any of RDKit's powerful features. Best of all, it's completely free and has excellent documentation. SMARTS is like SMILES with superpowers. While SMILES describes specific molecules, SMARTS describes patterns that can match many molecules. Think of it as regular expressions for chemistry. The pattern *OH bracket matches any hydroxyl group. #6 equals #8 matches any carbonyl, regardless of what's attached. Wildcards make SMARTS flexible. #6 means any carbon regardless of hybridization, * means any atom, R means any ring atom. This is incredibly powerful for virtual screening. You can search millions of molecules for specific functional groups or pharmacophores in seconds. Let's recap what we've learned. SMILES gives us a text-based language to represent molecules that computers can process. In CH, I provides unique identifiers for unambiguous molecule identification across databases. Molecular graphs enable powerful computational analysis using graph theory and machine learning. And RDKit puts all these capabilities at your fingertips with a simple Python interface. In Chapter 2, we'll build on this foundation to explore QSAR and QSBR, using molecular representations to predict properties like solubility, toxicity, and biological activity. I encourage you to practice converting molecules to SMILES and explore RDKit's documentation. See you in the next chapter.